So now let's go look at our sample. So we fill in a top half. When you're doing reflections, vertical reflections, horizontal reflections, and 180-degree rotations, we're going to be working with halves to begin with. Okay, so we fill in the top half with some arrangement of letters. And it would be, this arrangement of letters would be counted by your bell numbers. And then you have to decide, there's three possibilities when you do the reflection. The letter could go to itself. The letter could go to something that never appears in the top half, but I call a new letter. Or the letter could be, its image could be another letter that appears in the top half, an interchange. So for example, when you do this reflection, A goes to itself, B goes to X, it's a new letter, and look what happens to C and D. C reflects to D, and D reflects to C. They interchange when you do the reflection. And those are the three basic possibilities this whole game, when you're doing this counting, works with. Okay. So let's see what we're going to do. How we're going to build this generating function. Okay. So what you do is you have to determine how many letter arrangements you can put in the top half. So you get this many. J counts the number of letters I can put in the top half, from anywhere from 1 to 2n squared. Because I'm working with a 2m by 2n, I'm working with an even square. There's no fixed center column, center row. This symbol, do you know what this symbol is? I know Professor Zauber knows.
Is that the Stirling number as well?
Yeah, it's the Stirling number of the second nine, yeah. And it's basically the way you count them. It's saying it's 2n and I have j such letters. Taking the size of 2n and making it into j subsets.
That's the Knus.
Yes, it's Knuth's notation. Yeah, I know. So it's a bit. Yeah, so you could also call this as capital S 2nj if you prefer. I don't know which. You like that one, yeah. All right. Unfortunately, all the papers this was published in, they wanted it this way. I don't know.
No,
Yeah. Okay. But it. Okay. So that's basically how many ways you can fill the top. Then you look at the letters in the top, and you want to count how many ways you can form interchange pairs. And so you can have no interchanges all the way up to the floor of J choose 2. Now I don't write the floor traditionally. Some people don't have that top, but this is the floor. And then you can count the interchanges using this product, which we'll explain in a minute. And then what's left over, the letters that I haven't interchanged either go to new letter, like A goes to X, no, A goes to A, or goes to itself. So either what's left over must be, there's two possibilities. It must go to itself or to a new letter. And hence that's why you have the two. Okay, now I should note, if S is 0, you just ignore this product and you just jump to that. And when you expand this product out, you can simplify it. And it simplifies down to all my formulas. Will simplify down to having something like this. So, and just to help you understand the interchange, here's a test. Here's our 2 by, this would be basically, this should be a square. Forgive me if this isn't a square. The idea is if you want to, you could extend this out a little bit more to get a square. Okay, so here's our sample. And if J is 4 and S is 1, you want to count how many interchange pairs you can have. The answer is 6 because, well, can you tell me what they are? It's not supposed to be too hard. Yeah, AB. AC, yep, of course. Yep. Yep.
C.
Thank you. Yes, of course. Now, when you have 2 interchange pairs, you can only get 3 because basically once you pick the A, you're basically done with what's remaining. AB goes to CD, AC goes and, because these have to appear in conjunction, AC goes to BD and AB and BC. So they appear in pairs. In other words, you have a string that has order, and you've got to take away that many orders. That's why I have to divide by S factorial. So once you do all that geometric construction, you get this nice little nifty formula. And then you just have to use some generating function techniques to sum it. Okay. And so when you do that, here's your answer. You're going to get exponential generating functions. And I finally realized this is kind of a variation of what Herb calls the exponential family technique. So all of these are general this way. Okay? And if you know something about, I'm not going to write it down because of time constraints, if you know something about the generating function for Bell numbers and second Stirling numbers, you basically put this in, the t variable in, and then you just use those facts, the binomial theorem and the exponential sum, and it falls into place. Okay? So, once you have all those three possibilities, you basically, that's all we're going to do for the next couple times, for like the rest, for the vertical and horizontal symmetries. Whereas the next thing we have to do is we have to look at squares with an odd number of rows. Well, there's one slight problem. They have a fixed column, or fixed row. So you could rotate and get a column if you want to, but a fixed row. And so what you have to do is you have to analyze that row a little more carefully. But the idea is still roughly the same. You fill in the top, step one. You determine how many letters from the top must appear in the middle. You want to put into the middle row, okay? So here I just decided I'm going to throw A in the middle row. Now notice what happens when A goes in the middle row. I want to make sure it's symmetric when you do the reflection, so A must go to itself, and it determines what's going to happen to A at the bottom. Finish the middle row with stuff that never appears anywhere else. And then what's left over, you just do the horizontal, what we did before for the even case. You basically say, okay, how many letters left over? I want to say whether they go to themselves, whether they reflect, or whether they interchange. And if you do all that, you're going to get something that looks like that. Now, at least get nastier as you get along, but it's the same kind of game. I kind of like how you build this from little pieces.
So the odd is more complicated than even?
Yes, because you have that extra row fixed, and that's where the y comes in. No, the x comes in. That's why you get two variables for this. Everything that has a fixed piece gives you another variable. Every fixed row, every fixed column. So I made some of these things up when I have all the symmetries, and they have to have three variables because I have a row and a column fixed. But I'm not going to show you that. They get nasty. Those you have to sum like 56 things carefully. And by the way, yes, I can check these. I have a program that at least checks a priori, not with the generate, but constructs with maple symmetry, and then you can compare the generating function coefficient. So that's another way I check these.
So everything is tested?
Pretty much. For locate, yeah, for a certain amount. I mean, for lower, up to like 4 or 5. But yeah, I mean, you can't. It blows up. I need more space, though. I need huge memory to test higher. But the same game comes along. You basically have to just put in an extra variable. Sure. Now I said we did horizontal symmetry. Did we do vertical symmetry? Remember, this is a square. Yeah, so you just had to rotate it, and yes, we've done vertical symmetry. So now we've already taken care of H for even cases and odd. We've taken care of V. We have to now look at rotation, 180-degree rotation. All right. Well, I claim if it's an even square, you already took care of it. Same argument I use for HN works for R to the 2n. So all I'm going to have to look at is for an odd square when I do 180-degree rotation. Okay, and now how do you think I'm going to subdivide such a thing? Into halves or quarters? No, you have one ahead. Now, quarters are 90. I'll show you. You're still going to use a half. Okay, you're still going to use a half. But here's your half key. It has to be an L-shaped half. Because the fixed thing is the center point. I've got to work around that. And so you're going to play the same game. You basically fill in the dark pink fixed half with letters, determine which of those letters rotate to themselves, rotate to a new, interchange, and then you determine how to fill in the middle square. So either it's something that rotates to itself or a new letter. Okay, same game. We had time, I have you fill this in, and you get this generate this summation,